Okay, so I wrote already the formula here. Take some time to look at the notes because it's not a hard exercise, but I just don't want to do it right now in the presentation. But take a look at the proof of this formula, how you actually show that the Laplace of t minus a is given by this formula. So this is in the formula sheet. You don't have to know the proof for the exams, but it's a good exercise to see how that comes to be. It's a very simple integral. So when you take the Laplace of just the step function, that's the formula for the Laplace transform, e to the minus as over s. I should just mention something important. When you manipulate these Laplace transforms, aim always to have this minus negative explicitly stated on the outside of that coefficient. You'll see later what I mean in some examples, because the time value where this function acts upon, it's easier to see if you have the minus out. There will be a special formula called the Delay Theorem, which we'll talk about soon. But in general, aim to write that minus explicitly out. Doesn't matter what you have here as a coefficient of s. Have that minus explicitly out of that coefficient. So minus is part of the formula, just to make it clear. So let's do an example similar to the one before. So let's say when you write a piecewise function in terms of Laplace transforms, in terms of step functions, let's say it's equal to 7 minus 3 step t minus 1, and then plus 9 step t minus 3, let's say, and then minus step t minus 7. So as long as you have only constant coefficients in front of the step function, then to find the Laplace transform of this function is just a matter of using linearity property and then, of course, this formula. So let's say I want to find L of f of t. Well, that's going to be, again, with the linearity property, that's going to be 7 Laplace of 1 minus 3 L of step t minus 1 plus 9. You move the coefficients out of the Laplace transform. That's what you do here, right? So step t minus 3, and then minus L of step t minus 7. Again, you could do this in your mind and write the answer right away. If it's a matter of just pulling out the constant in the linearity property, you should be able to do this already in your mind after you practice a couple of times. So L of 1, look at the table, is 1 over s. And now for each of these, you apply this formula. Step t minus 1, step t minus a. Right? So that's going to be e to the minus 1 times s over s plus 9 e to the minus 3s over s. Right? Because now a is equal to 3. And for the last one, minus e to the minus 7s over s. Okay, so things are nice so far, actually, believe it or not, because this is just a single formula. But if you remember the previous example in the previous part, the very last example, it is possible that the coefficients of the step functions are not constant. So what do you do if you have to take the Laplace transform of some function of t times the step function? Because I mean, this can happen in reality, right? I mean, what if what you want to return, I mean, what you want the function to return when t equals 5 is not a constant value, but a function. And you'll see an example later as well. Maybe you want the current to increase gradually, let's say, not just to have a single value when t equals 5. So that means you multiply the step function by a function of t. Well, there is not an easy way out on this. I mean, there is a formula, which actually is not difficult to apply, but there is a formula which actually it's a little bit more tedious than all the others. So it's a Laplace transform designed to handle these type of situations. So I don't want to make people feel bad already about it, because it's not actually overly difficult, but it's one of those things that requires some practice. That's the magic thing. I mean, by the way, there's no easy way out in many other situations like this. Some stuff just require practice, but once you achieve that practice level, then it's going to be easy. So the formula that it's needed for this type of Laplace transform is the so-called Delay Theorem. And again, have the table in front of you, the table of Laplace transforms. So you can see it there. It states that the Laplace transform of a function applied to t minus a, so a function at t minus a, times the step function at the same time value, t minus a, is equal to big F of s e to the minus as, where big F of s stands as usual for the Laplace of f of t. So we're going to have to practice with this formula for a while before we move on. Because if you look carefully, in order to apply it, you need to write your function in a specific form. See, notice here I said g of t times step t minus 5, right? So I mean, you need to write your function here as a function of t minus a. Either it's already written like that, or you have to write it using some algebra manipulations. But whatever you do, you have to write it in that form. And then on the right hand side, you have the Laplace transform of the same function, but with t minus a replaced by t. So the application of the formula requires some substitutions at various stages in the process, from left to right or from right to left. Nothing really special happens here. You will take a Laplace transform at some point, right, using the table or other techniques you learn, but you just have to remember that at some point you'll have to make some substitutions, right, because here it's L of f of t, whereas here is f of t minus a. So I'm going to split this lecture at this point in two parts. How do we apply the formula from left to right when you take the Laplace of this, and then how do you apply the formula from right to left when the goal is to take the inverse Laplace of something like this. So when you have a function in s times e to the minus as. So let's say, let's write it as a subtitle here, the Delay Theorem from right to left, excuse me, the other way around, from left to right. So when you take the Laplace transform, so from left to right, the way the table is usually written, right? So I have on the left side f of t minus a, step t minus a, and I want the answer, right? I want to put the answer for this question. So there are actually essentially a couple of steps. The first thing to do is to replace t minus a with t in f of t minus a. So you make that substitution first. You make sure you have this written in the form of f of t minus a. You make the substitution, and this becomes f of t. And then on the second step, you compute the Laplace of f of t. So you compute big F of s, Laplace of f of t. And that's really all there is to it. Once you're done with that, you put the answer right here, f of s times e to the minus as. So e to the minus as, if you want, corresponds to the step t minus a. If you look at from left to right, step t minus a will cause the appearance of e to the minus as. And all you got to do is to collapse t minus a into t to make the substitution, take the Laplace of that resulting function, and multiply it by f of by e to the minus as. And that's going to be your answer. Like I said, practice makes perfect. So let's write a couple of examples. So suppose I have to compute the Laplace of t minus 3 squared times step t minus 3. So I already wrote it in an appropriate form so that it's easy to apply in this configuration. Now have the formula sheet in front of you because you will need it. So in the first step, like I said, you take this function t minus 3 squared and you replace t minus 3 with t. So this becomes t squared now. So pause for a moment and make sure you understand this step, okay? I mean, this is what we mean by substituting t minus a with t into the function that is multiplied by the step function. Okay, so in your case, that results in t squared. This is your f of t in the formula. That's your f of t minus a. This is your f of t. Okay, make sure you understand that. What do you do now? Well, on the second step, you take the Laplace of t squared. And again, if you look at the formula sheet, this will be 2 factorial over s to the power 3. And the hard part is over, right? Now you write it here on the right-hand side. 2 over s to the power 3 times e to the minus as, which is in your case e to the minus 3s. Substitution, taking Laplace, write the answer. Again, from left to right, substitution, take the Laplace of what you get, put the answer over there. That's the order of operations here. Let's move on with another example. Let's do a trigonometric function. So let's suppose you have, let's say, Laplace of sine of t minus 7 times step t minus 7. Notice again, I purposely wrote the problem in the appropriate form for the delay theorem. We're going to do an example when that's not the case, when you have to do a little bit of algebra tricks to write it in that proper form. Okay, what is your f of t minus a? Well, that's sine of t minus 7. Make the substitution, that becomes sine of t. T minus 7 replaced by t. Take the Laplace transform of L of sine of t. That's going to be 1 over s squared plus 1. Look at the table if you don't remember. And then write the answer. 1 over s squared plus 1 e to the minus 7s. It's just mechanics, okay? Just practice. Nothing special. What makes it confusing in the beginning are these substitutions. And people who have troubles understanding how to make substitution in functions, this is where the problem arises. But make all the effort you need to understand what the function is and what it means actually to change the variable in a function. You do that actually in other contexts, remember. Use substitution, some other situations in calculus when you do that. That's what it is here. It's just a substitution. Here's an example in which you need to do some algebra before you actually apply the delay theorem. So what if I have to compute the Laplace of e to the, let's say, e to the 2t step t minus 3, let's say. This is a little bit trickier because if you look carefully, this is not in the proper form. Okay, you need this to be as a function of t minus a. Now, I have t minus 3. I need to write this as a function of t minus 3. So I need to produce by algebra means, I need to write this as a function of t minus 3 without changing the value of the function. So what you do is, inside here, inside the exponent, subtract and add 3. And break down this exponential so that it's written in the form of a function of t minus 3. So again, you need to see this as something in t minus 3, subtract and add 3 to produce it, and then break down the exponential like this, e to the 2 quantity t minus 3 times e to the 3. Okay, so in order to apply the delay theorem, you need to write that e to the 2t as e to the 3 times e to the 2 t minus 3 in the parentheses step t minus 3. You need to put it in the proper form like this. Now this e to the 3 becomes an extraneous constant. You can take it out when you apply the Laplace. That's not a problem. But let's do let's perform the delay theorem now. So let's actually pull that constant out. So this is e to the 3L of e to the 2 quantity t minus 3 step t minus 3. And now the function that constitutes f of t minus a is e to the 2 t minus 3. Make that substitution by replacing t minus 3 with t, and then take the Laplace of that, which is 1 over s minus 2, right? The Laplace of e to the 2t is 1 over s minus 2. So finally, the answer to the problem, I'm not going to write it here, but the answer to this will be e to the 3, 1 over s minus 2, e to the minus 3s. Later you can combine these exponentials if you want. That's not mandatory, but it looks nicer. And it's e to the 3 quantity 1 minus s. But that's just a simplification, doesn't matter. You can leave this e to the 3 outside. But just to summarize, this one requires this little algebra trick because you need to write it in that form. Okay, so with that in mind, let's move on with the next part on how to use the formula from right to left. And you will see that, because you need that also, right, when you take the inverse Laplace of these functions. You will see that the process is really in reverse. I mean, it's the same type of work, but in reverse. You will start by taking the inverse Laplace, because again, let's go over the main steps from left to right. You have a substitution, t minus a with t, then you take the Laplace transform of that. From right to left is the opposite process. You will take an inverse Laplace of this, then you're going to replace back t with t minus a, and then you're going to write the answer on the left side. It's really the same thing in reverse. But let's see how that looks like with examples in the next part.